if we think of the situation we just looked at here as the capacitor discharging through the generator, we have the small resistance of the generator, which in other places we've estimated to be in the order of 10 or 20 ohms. And in fact, that's what we did when we got the data here. We see that our estimate of the resistance from the time constant, RC, was 5 ohms. So we estimate a 5 ohm resistance from the fact that the delta T from 10 volts to 3.7 volts was 2.7 seconds. Now, we know that, okay, this is the case if we hold the crank of the generator. We notice that if we hold the crank, the current falls and the voltage falls more rapidly than if we don't hold the crank. Now, why is that? If we don't hold the crank, and really I should have probably drawn a capacitor here to discharge through the coil, but we'll see in a minute that this is what's going on anyhow. We have a coil of wire. Now if we think of a source, let's say rather than the capacitor, and we have a switch here, if we suddenly throw this switch, then a current suddenly starts flowing in the circuit. What happens when the current suddenly starts flowing through this coil of wire? Remember again that if this coil represents the generator, if we had a battery hooked to the generator, then that battery would have to push a current through the coil. Now the coil just consists of wire, it doesn't have much resistance, so we might expect that the current will just very, very rapidly go up to a very high level, whatever small resistance there is in the wire here. But that's not what happens, and the reason is because when we close this switch, the current has to build through this wire. It starts at 0 and it's going to build up to some maximum. Now when that happens, as the current goes through the coil, we have this situation. The current going through the coil in this direction is going to give us a magnetic field in this direction. Now, once the magnetic field is set up, or well, once there's a magnetic field here, then there's a flux through these coils. So we have a changing flux through the coil. Okay, so that as the current I builds, the magnetic field builds, and the flux in the coil builds. Now what do we know about flux changing in a coil? Well, we know that there's a voltage that's equal to the rate of flux change. Okay, so if I is increasing, then the magnetic field is increasing, so the magnetic flux phi is increasing. From that it follows that the voltage, which is just your d phi over dt, your change of flux over your change in time, that voltage has to rise, and that voltage, it turns out, resists the increase. Now if you get very careful about the direction of the flux through here, we see that as the flux increases, it induces a voltage in this direction. Okay, so the voltage from the source is pushing this way. The voltage that we get from the changing flux pushes back this way. Since we have a flux or a voltage pushing back this way, the current is not going to be as great. Also, we see that we can't change the current really, really fast, because if we did, d phi dt would be really, really large, greater than the voltage that's pushing the current through, and there would be no current, or there would be a negative current. That actually can't happen. The voltage that we're pushing back with can't be any greater than the voltage we're pushing forward with. But the point is, we have this, what we call inductance, okay, where the coil, by the changing current in the coil, produces a flux that changes, and that changing flux induces a voltage in the opposite direction. Now that explains why the current falls more slowly if we allow the crank to move on the generator. because what's happening is as the crank moves and the current flows through the generator, we have a flux in the opposite direction, well, a flux change, and the rate of flux change will be opposing the flow of the current, so that not as much current flows through the generator from the capacitor, and the capacitor discharges more slowly.